our next speaker is, and I hope I don't butcher your name too badly, Swetabh Patel is our next speaker. He's a researcher at the University of Minnesota. He's also in the Department of Soil, Water, and Climate, and his work includes research into soil fertility and plant nutrition. I understand you're relatively new here, so welcome to Minnesota.
So yeah, I'm excited to be here, and it's good to see such a good turnout and people interested in learning more about nitrogen. So as mentioned, I'm relatively new to University of Minnesota. I joined back in October 2024. And I'm excited to present some of my work related with nitrogen and nitrogen best management practices that I did when I was in University of Nebraska before moving to Minnesota. And I hope that the findings and insights that I present today would somewhat be applicable to Minnesota conditions as well. So before we dive in, let me ask you a question. How many of you consider that nitrogen sources, stabilizers, and best management practices have an impact on A, nitrogen use efficiency, B, crop yield, C, economic returns, D, water quality, or do you think it impacts all of the above? I see some hands, all of the above. That's good. So yeah, if you are unsure about it, don't worry. By the end of this presentation, you might have some more insight on how nitrogen sources and stabilizers impact all these parameters. So since today's talks are mainly focused on nitrogen and how we can prevent nitrogen losses in the soil and improve nitrogen use efficiency, I want to share the chemistry of fundamental nitrogen fertilizer transformations that happen once the fertilizer is applied to the soil. In this case, we'll take an example of urea. Urea, which is mainly in the form of ammonia, and once urea is applied to the soil, it converts into ammonium, and ideally urea must be immediately incorporated into the soil through rain or water, but without insufficient rain, there would be substantial losses in the form of ammonia volatilization. In the next step, ammonium is converted to nitrate through the nitrification process. Both of these nitrogen forms, which is ammonium and as well as nitrate, can be taken up by the plants, but the uptake of nitrate is more rapid because it has higher mobility as it is negatively charged and can move freely into the soil system. So the roots can easily interpret the nitrate and can actively take it. However, ammonium is positively charged particle and is tightly held by the negatively charged soil particles. And that's why its mobility in the soil is not as fluid as compared to nitrate. Ammonium is also considered as a more stable form of nitrogen pool among the two nitrogen forms due to its mobility in the soil. So if the nitrogen stays longer in an ammonium form during the May and June period, which is also the period of rapid potential nitrogen loss, it is protected from the potential leaching losses when the roots are not actively taking up the nitrogen. Suppose nitrification occurs immediately after fertilizer has been applied to the soil and most of the nitrogen is available in nitrate form. In that case, the chances of nitrogen losses through denitrification or nitrate leaching to the groundwater significantly increases. So the groundwater nitrate contamination has become a significant concern across several regions in the United States due to mainly because of the excessive use of synthetic fertilizers and asynchronization between the nutrient availability and crop uptake. However, we can decrease the nitrogen losses by following some of the best management practices. And one of the most effective, innovative, and direct way to address these challenges is to follow the 4R nutrient stewardship concept, where we apply nitrogen from the right source, right rate, right time, and in right place. These four central components, when used together, provide a unified approach for improving nitrogen use efficiency and minimizing nitrogen losses. Today, I will primarily be focusing on nitrogen sources as well as integrated use of best nitrogen management practices in order to reduce nitrogen losses. So some of the management practices, if applied correctly, have the potential to alleviate the nitrogen losses as well as improve the crop productivity. For example, use of manure can improve the biological as well as physical characteristic of the soil, as well as improve the crop productivity by supplying the essential nutrients. Wood chips, when used as mulch, can act as a high carbon source and can improve the physical property of the soil, as well as reduce the nitrogen losses by tying up some of the nitrogen in the soil. Cover crops are well adapted practices which can help protect the soil in the absence of row crops, and they can also scavenge some of the excess nutrients that are present in the soil. And last, split nitrogen application is also a part of BMP, which helps improve the nitrogen use efficiency by synchronizing the nutrient availability and crop uptake. So we will look further into these later in my presentations. Let's talk a little bit about nitrogen sources. So there are many nitrogen sources in the market, and most are ammonia-based fertilizers that convert to nitrate once they're added to the soil. Nitrogen inhibitors such as Anserve, Trident, and Instinct these are the products that can help retain the nitrogen in ammonium form for a longer period of time, and thereby help better synchronize the nutrient availability with crop uptake in delaying the nitrogen conversion to nitrate. So how do these nitrogen stabilizers work? What are the different types and what are the mode of action? So, well, there are two different kinds of nitrogen stabilizers or inhibitors. The first one is urease inhibitor, which inhibits the conversion of urea to ammonium and protect it against the ammonium gas losses when urea is placed over the soil surface and there is not enough rain to incorporate that urea into the soil. The active ingredients in products with urease inhibitors are NPPT and NPPT. These active ingredients are found in products with trade names of Agrotan, Limus, and also some other slow-release fertilizers like Nfusion and ESN that also contain NBPT and NPPT. The second form of nitrogen stabilizer inhibitor is called nitrification inhibitor, which inhibits the conversion of ammonium to nitrate. And the active ingredient in this kind of products containing nitrification inhibitors are nitropyrene and DCD, which can be found in a variety of products such as Anserve, Guardian, and Instinct. So these nitrification inhibitors can help reduce the nitrogen losses that we often see in the form of N2O or N2 gas emissions through denitrification or leaching losses as well, especially when crops are not actively taking up the nitrogen. So by strategically choosing these inhibitors, we can better synchronize the nitrogen availability to crop uptake. So in the previous slide, I went over the different types of nitrogen stabilizers. And in this slide, I want to show how these nitrogen, which is released from the stabilizers, work in accordance with the crop nitrogen uptake. So this graph here shows the crop nitrogen uptake during a typical corn growing season. The area under the curve here shows the plant nitrogen uptake. You can see that plant actively take nitrogen mostly between the V9 and V18 growth stage from late May to July, when we need to ensure that nitrogen is not limited for the plant growth and there's enough sufficient nitrogen available. However, suppose you applied conventional nitrogen fertilizer in the last fall or early spring, and there is a heavy rainfall in the spring, then most of this nitrogen can be lost with the heavy spring rains, and plant may become nitrogen limited. This is what we call unstable nitrogen, which is shown in the red line here. However, if we apply the nitrogen stabilizers, then in that case, most of the nitrogen can remain in the stable form until the crop needs it in the late June and July, in June and July period, which would also minimize the nitrogen losses. And this we are calling as a stabilized form of nitrogen, shown here in the dark blue line. So far I have talked about the use of BMPs, nitrogen sources, and stabilizers, and how they can potentially reduce nitrogen losses and increase the nitrogen uptake. Now I'm gonna share some of the studies that I did where I looked at different nitrogen sources and inhibitors. Here's the first study, which is called Integrated Best Management Practices to minimize nitrate leaching in corn. So in this study, we looked at the integrated use of manure, inorganic fertilizer, cover crop, and soil carbon amendment to help reduce nitrate leaching as well as improve corn productivity. So this study was conducted at Haskell Ag Lab at Concord, Nebraska, which is in the northeast part of Nebraska. In this region of this state of Nebraska, we have a high level of nitrate contamination in the groundwaters. A lot of counties in this region have more than 15 ppm of nitrate in their groundwater. So uh, this study was funded by USDA and it started in 2022. And the funding ended in 2024, but I believe the plan is to keep going and at least collect some of the basic fundamental parameters such as crop yield and nitrate leaching data. So this study, today I'll be presenting data from 2022 and 2023 of this study. And this study was conducted for a continuous corn system in a sandy loam soil. So in this study, there were a total of 8 treatments, 4 treatments with beef manure and 4 treatments with inorganic fertilizer. The treatments with beef manure were beef manure only, beef manure with wood chip as cover crop, wood chip as mulch, beef manure with cover crop, and beef manure with wood chip and cover crop. Similar treatments were there with the inorganic fertilizer, so inorganic fertilizer only, inorganic fertilizer with wood chip, inorganic fertilizer with cover crop, and inorganic fertilizer with wood chip and cover crop. However, in fall cover crops were not planted until the fall of 2022. So there was no cover crop effect from the data 2022 data. And the cover crop that we planted in fall 2022 did not establish well. So there was, again, no cover crop effect in 2023 data as well. So today, I'll only be presenting these 4 treatments in my data. So each treatment in this study received the same total amount of nitrogen in the season, which was calculated every year using the UNL's nitrogen recommendation. And all plots in this study uniformly received 40% of their total nitrogen in the form of agrotan urea, which was applied at planting, which was broadcast applied at planting. And rest 60% of the nitrogen was either applied in the form of beef manure at planting for the manure plots, or in the form of UAN, which was side dressed at V6 stage for the inorganic plots. Wood chips were applied right before planting at the target rate of 14 tons per acre. And then we installed 2 lysimeters in each plot at the depth of 4 feet, and then water samples were collected throughout the growing season. We also collected in-season soil samples in 2023, and the yield was also measured at the time of harvest. So this figure here shows the total nitrate and ammonium availability in in-season soil samples that were collected in 2023 at the depth of 0 to 12 inches. And in this graph, the circles here represent the manure treatments, and triangles represent the inorganic fertilizer treatment. The solid shapes indicate the treatments without wood chips, whereas the open shapes represent treatments with wood chips. The average nitrate and ammonium availability, as you can see, varied during the growing season, with higher nitrate early in the season and increased ammonium later in the season. Manure and organic fertilizers had a similar nitrate and ammonium levels, whereas wood chips, when used with manure or inorganic fertilizer, reduce the early season nitrate availability, indicating the potential nitrogen immobilization. This suggests that wood chips, being a high carbon source, might be tying up some of the nitrogen early in the growing season, but their effect on the overall nitrogen availability needs to be further investigated. So this graph here shows the corn yield data from 2022 and 2023. In 2022, we did not see any effect of mulch on corn yield when it was used with either manure or inorganic fertilizer. However, in 2022, The manure had slightly lower yield as compared to the inorganic fertilizer, and the yield reduction with manure seen in 2022 could be a result of a very dry condition in 2022, or because corn was planted first and then manure and wood chips were applied on the top of corn that was already planted, which caused a thick soil cover. And we saw that corn had some trouble coming out of that thick layer of manure and wood chip. So we learned from this mistake, and in 2023, we applied the wood chips and manure, and then we went ahead and planted corn using a row cleaner. So when we look at the 2023 yield data, we can see that mulch negatively affected the yield when used with both manure and inorganic fertilizer, but there was no yield difference between the manure and inorganic fertilizer treatments. These graphs here show the total seasonal nitrate load in 2022 and 2023. The treatments here are shown on x-axis, while the area-based nitrate leaching is shown on the y-axis in pounds per acre. Since nitrogen in this study was applied using the best management practices, you can see that the total seasonal nitrate load is low across all the treatments. Graph on the left-hand side shows the total seasonal nitrate load as affected by treatments in 2022. And you can see that mulch had no significant effect on the seasonal nitrate load in 2022, while manure significantly reduced the total seasonal nitrate load by 80% as compared to inorganic fertilizer treatment. If we look at this total seasonal nitrate load data from 2023 growing season, we can see that in 2023, there was no significant effect of treatments on total seasonal nitrate load. However, a pattern similar to 2022 was observed where manure treatment seems to have decreased the total seasonal nitrate load by 70% as compared to inorganic fertilizer treatments. Here I have not shown the data for the fall residual soil nitrate, but there was no treatment effect on the false residual nitrate, and it averaged about 10 pounds per acre in 2022 and 4 pounds per acre in 2023 across all treatments. So based on these results, we can say that complementary use of manure as nitrogen fertilizer source can help further reduce nitrate losses as compared to use of inorganic fertilizers only. Here are some conclusions from the study that I just presented. We can say that use of manure has shown to be a valuable tool for reducing nitrate leaching. And unlike inorganic fertilizers, manure provide a slower, more synchronized release of nitrogen, which allows for better crop uptake and minimizes nitrogen losses to the environment. The second is use of wood chips as a surface mulch may reduce the early season nitrate availability and corn yield without having any significant impact on the nitrate leaching reduction. And then use of synthetic fertilizers may increase corn yield, but also pose a higher risk of nitrate leaching. So by integrating manure with inorganic fertilizers, we can achieve a balance between sustaining yield and reducing environmental risk. And this approach helps enhance the nitrogen use efficiency while mitigating the nitrogen losses. Moving on to the next study. In our second study, we examined the effects of nitrogen source, herbicide, and nitrogen stabilizers on nitrification and corn yield. This study was conducted by a master's student in our lab. And in this study, we sought to answer two questions. First is, do nitrification inhibitors effectively reduce nitrogen losses? And second, how do nitrogen sources interact with inhibitors and herbicides to influence corn yield and nitrogen use efficiency? And it's vital to understand these interactions because for developing good nitrogen management strategies that will minimize environmental losses while maximizing the crop productivity. Here in this study, we included herbicides because in some studies, it was shown that herbicide can act as an inhibitor and reduce nitrification. So this study was conducted at South Central Ag Lab at Clay Center, Nebraska, and was conducted for 2 years under rain-fed conditions on a silt loam soil. This study was recently published in Soil Science Society of America journal. So in case if you need further information about this study, you can refer to our published article. So in this study, in addition to a zero nitrogen control treatment, we had 4 nitrogen treatments, which were anhydrous with and without nitrification inhibitor, urea with and without nitrification inhibitors, and all these nitrogen treatments received a rate of 151 pounds nitrogen per acre as per the UNIL and recommendation. Nitrogen was applied in the spring in both years to test the effect of pre-emergence herbicides on nitrogen transformation. We had all these treatments separately treated in blocks with Acuron, Resicor, and no pre-emergence herbicide. It is also important to note that all the blocks in this study received a post-emergence herbicide as well. The crop rotation in both years was corn following soybean. And during May and June of each year, we collected the weekly soil samples and analyzed them for nitrate and ammonium. Let's jump into the results now. The graph here shows the effect of nitrogen source and inhibitor, nitrification inhibitor on soil ammonium during the May and June of each year. As you can see, we did not find a significant effect of herbicide on nitrification, so I'm not presenting the herbicide effect results here. So in 2020, the anhydrous with inhibitor retained significantly higher ammonium as compared to anhydrous with no inhibitors on 5 of the 8 sampling dates, whereas this difference was only significant at 2 of the 8 sampling dates in 2021. Whereas urea with inhibitor retained significantly higher ammonium than compared to urea without inhibitor at only 1 of the 8 sampling dates in 2020, whereas no significant differences was found in 2021. So these results indicate that there was inconsistent effect of inhibitors on stabilizing nitrogen. But interestingly, when we average across all the sampling dates, anhydrous with or without the inhibitor use retained significantly higher amounts of ammonium concentration, which was about 340% to 300% as compared to urea with and without inhibitors in 2020 and 2021 respectively. So while inhibitors showed some potential for reducing nitrogen loss potential, findings suggest that a more crucial role in maintaining nitrogen retention than inhibitors alone is the use of nitrogen sources. Again, this highlights the importance of choosing the right nitrogen source for effective nitrogen management. Again, this table here shows the percent of ammonium left at certain days interval after the fertilizer application. And you can see that nitrification inhibitors reduce the nitrification by 2 to 15% when they were used with anhydrous, as compared to 1 to 10% when they were used with urea across all the sampling intervals. Across all the sampling intervals, anhydrous with and without inhibitor retained more than 50% of ammonium as compared to urea with and without inhibitor. Again, this data here shows emphasizes a more prominent effect of nitrogen source as compared to inhibitor. These graph here shows the impact of nitrogen source, inhibitor, and herbicide on corn yield in 2020 and 2021. And when examining the impact on corn yield, we found that nitrification inhibitor did not affect the corn grain yield in both years. However, in 2020, an interaction was observed between nitrogen source and herbicide application. Specifically, urea treatments without pre-emergence herbicide resulted in lower grain yield as compared to anhydrous with and without inhibitors and no pre-emergence herbicide. This was possible because in 2020, there was a delay in application of post-emergence herbicide, which led to a prolific growth of weeds, and these weeds were able to take up the nitrogen from the urea that was applied on the surface. However, in case of anhydrous, which was injected deeper into the soil, the weeds may not have access to the nitrogen from the anhydrous, and therefore the impact of weed was not seen on the ammonium anhydrous treatments. Uh, when we look at the 2021 data, there was no interaction or effect of treatments on yield, because in 2021, the post-emergence herbicide was applied much earlier in the season, and uh, therefore there was a better weed control, and weed did not interfere with the treatments. Again, these results emphasize that banned application of nitrogen, such as anhydrous ammonia injection, may help reduce the nitrogen uptake by weeds as compared to broadcast application, which happens in case of urea. Then we also calculated the effect of nitrogen source and inhibitors on economics. And this table here shows the yield, nitrogen use efficiency, and marginal net return among the anhydrous and urea treatments with and without inhibitors. The red and green colors here indicate the significant differences between nitrogen sources. And as you can see, in 2020, the anhydrous ammonia produced 18 bushel per acre more yield and generated $86 per acre additional income as compared to urea. So, uh, however, there was no significant economic differences observed in 2021. Again, this highlights the variability of nitrogen management strategies across different growing seasons. So one management may not be applicable to each year. So we need to base our management decision based on the seasonal variability as well. In order to further investigate the effectiveness of nitrogen nitrification inhibitors, multiple on-farm trials were conducted in southeastern Nebraska on fine textured soil. So here's data presented from 7 on-farm trial sites. The sites are on the x-axis, whereas the grain yield, nitrogen use efficiency, and partial profit are represented on the y-axis. And across these 7 site years, we found that there was no significant effect of nitrification inhibitors on grain yield or nitrogen use efficiency. However, nitrogen inhibitors did have a lower partial profit at one of the 7 sites. Uh, Next, earlier in this, earlier in study 2, I shared the results from our study showing that nitrogen sources could significantly affect the nitrogen losses. And some other studies have also demonstrated that importance of nitrogen source and placement on nitrogen losses. For example, one study conducted in 1991 showed that ammonia volatilization loss for different nitrogen sources and application methods with varying rainfall scenarios. Here you can see that the ammonia volatilization estimates for high-risk soil with pH above 7 is shown in this study, but some similar studies have also shown similar estimates for ammonia volatilization losses for lower pH soil. Here you can see that across all the nitrogen sources and placements, there would be less nitrogen losses if there is more than half inch of rainfall within the 2 days of fertilizer application. And however, these losses can be higher if there is no rain within the 7 days of fertilizer application. Again, if you look into the nitrogen application methods, then we can see that surface applied fertilizers, either broadcasted or dribbled on the surface, have more potential for nitrogen losses than the injected fertilizer. And when you look at among all the nitrogen sources used here, we can see that anhydrous ammonia seems to have lower ammonia volatilization losses as compared to other fertilizer types. So in order to summarize the findings of this study, we can say that overall in fine textured soil, using the right nitrogen fertilizer source can have more significant impact on protecting nitrogen and reducing nitrogen losses and economic returns than using the inhibitors. And then, though inhibitors showed potential for inconsistent effects and reducing nitrogen losses under the intensive rainfall conditions, we recommend a combination of right nitrogen source and nitrogen stabilizers in order to improve the nitrogen use efficiency. However, we recommend that the priority should be given to choosing the right nitrogen source over the nitrogen inhibitors, especially for the fine textured soil. Then here are some take-home messages from the both studies that I presented here today. First is complementary use of manure as a part of nitrogen management strategy has potential to reduce nitrate leaching while maintaining comparable yields to inorganic fertilizers. Second is while nitrogen stabilizers can offer an additional benefit in certain conditions, choosing right nitrogen source and maximizing and timing is very crucial for reducing the nitrogen losses and maximizing economic returns. And lastly, while nitrogen stabilizers and best management practices can enhance nitrogen use efficiency and their cost effectiveness should be evaluated to balance the productivity as well as sustainability. With that, I would like to thank you all, and I would be happy to answer any questions. Okay, so the question is, if herbicide had been believed to impact nitrification, why was the treatment applied post-emergence rather than at planting? So the herbicides that we used in this were pre-emergence herbicide. The post-emergence herbicide were applied to all the treatment irrespective to control the weeds. But like I said, in 2021, the post-emergence herbicide were delayed, and therefore we saw the problems of weed control. So in this study, we were looking at the pre-emergence herbicide and whether or not they act as nitrogen inhibitors. So we were looking to test that.
Anybody in the room have a question? Are there any new nitrogen product stabilizers on the market that might be coming in the next few years?
Well, they need to be tested first. I mean, I'm sure there are biologicals which we have not seen any consistent effects, but the most results that we have is from ESN and Instinct and Serve. So these are the products that has been widely tested. The new products, there's always new products coming into the market, but we cannot say anything until they have been extensively tested.
Good. Any other questions? All right, let's give them a hand. Thank you.
Thank you.